So now we will talk about second law of thermodynamics. Second law of thermodynamics. So before defining the second law of thermodynamics, I will just tell the first law of thermodynamics was the law of energy. So similarly, the second law of thermodynamics, it is a law of entropy. So in the later stage, we will talk about the definition of entropy and how it is useful in thermodynamics. So the second law of thermodynamics saying complete conversion of low grade energy into high grade energy is impossible. So according to the second law of thermodynamics, the complete conversion of low grade energy into high grade energy is impossible. So I will write the low grade energy. So whatever the heat energy we are getting from fuel or some other things, that is called low grade energy. High grade energy, high grade energy, maybe mechanical work, electric energy, electric energy. So this is these are the high grade energy. So according to the second law of thermodynamics, the complete conversion of low grade energy into high grade energy is impossible. So second law of thermodynamics are defined by two statements. So one is Kelvin Planck statement. So according to the Kelvin Planck statement, it is impossible for a heat engine to produce net work in a complete cycle if it is exchanging heat only with the bodies at a single fixed temperature. So I am again redefining the Kelvin Planck statement. It is impossible for a heat engine to produce a net work with heat interaction only with one reservoir. So I will suppose T1, that is we are calling it source, which is having high temperature, and here I am defining the heat engine He, and Kelvin Planck is saying it is impossible for a heat engine to produce work with interaction only with the one heat interaction only with the one reservoir, that is called source. Or in other words, it is impossible for a heat engine to produce work without rejecting any heat to the sink. So it's impossible. So that this one is the Kelvin Planck statement. Similarly, there is one more statement that is called Clausius statement. And according to the Clausius statement, it is impossible to construct a device which operating in a cycle will produce no effect other than transfer of heat from a cold body to hot body. So what Clausius statement is saying, suppose T1 is having high temperature. I can say T1 is greater than T2. And T2 here, and here there is a heat pump, we can say that. So what they are saying, Q1 here, oh sorry, will extract heat from a colder body and it will give to a hotter body. So it's impossible because we know the heat will flow from high temperature body to the low temperature body. And suppose if we want to transfer the heat from a cold body to the higher body, then we have to work on the system. Without doing work on the system, we can't transfer the heat from the cold body to the hot body. We'll start with some of the gate questions for clear understanding the thermodynamic fundamentals. So I am just taking some of the gate questions. So now I will take gate questions. I'm now taking the gate question which is asked in year 2009. Okay, it's based on thermodynamics. So first I am writing the question. A compressor undergoes a reversible steady state flow process. The gas at inlet and out of the compressor, the gas at inlet and outlet of the compressor is designated by 1 and 2. Potential energy and kinetic energy are neglected. Now we have to find out the specific work. Find specific work required to be supplied to the compressor for this gas compression process. So here we have to find out the specific work required to be supplied to the compressor for this gas compression process. So now we have to write down the steady state flow on per unit mass basis. So first I will we know what is the steady state flow equation, which is based on per unit mass basis. So I will write the steady state equation, that is del Q equals to del H plus del W. Here I am not considering the kinetic and potential energy. Now in that case, uh, we know we have to consider the reversible steady state flow process. So we also know this thing. We are having one more equation. It is in terms of enthalpy. H equals to U plus PV. We know that is H equals to U plus PV. So del H will be del U plus del PV, and if we further write this thing, del H equals to del U plus PdV plus VdV. And we are having one more equation, that is del Q equals to del U plus PdV. So in place of del U plus PdV, I can write del Q. So del H equals to del Q plus PdV. So now I can write minus V dP equals to del Q minus del H. I am having this thing. If you see this thing here, del Q equals to del H plus del W. So I can write del W is nothing but del Q minus del H. And if you see here, del Q minus del H is nothing but minus VdP. Or del W is nothing but minus VdP. So now we integrate it and we will get 122 VdP. So the correct answer is specific work done in case of reversible steady flow process is integration of VdP. So the correct answer will be 1 to 2 VT. Remember one thing in the in non-flow process, the work done generally defined displacement work is generally defined by PdV, but in case of flow process, work done is Vd. So that is the difference between non-flow and flow process in terms of work. Now let's take another problem which is asked in GATE 2008. 2008. So I am just writing the problem. A balloon balloon containing an ideal gas is initially kept in an evacuated and insulated room. The balloon ruptures and the gas fills up entire room. So we have to find out which of the following statement will be correct. So now we will consider this process. Here the room is evacuated room. So the kinetic energy of gas in vacuum will be constant. So temperature will be constant in that case, because if kinetic energy is constant, then temperature will remain constant, because temperature will depend on the kinetic energy. Similarly, internal energy is function of temperature, so internal energy will be constant. So if you see what will happen, internal energy will be constant, and now we will talk about enthalpy. H equals to U plus EV. Now we know the internal energy is constant, and what about PV? So here it is mentioning in the problem, say insulated room, so no heat transfer will take place, so temperature will be constant, so this PV will be constant. So H will be constant in that case. So we can say that correct answer is both internal energy and enthalpy of gas remain constant. Take another problem which is asked in GATE examination. So I am taking a problem of GATE AME 2008. I am just writing the problem here. A rigid insulated tank is initially evacuated. The tank is connected with a supply line through which air passes at 1 megapascal and 350 degrees centigrade. A valve is connected with supply line is open and the tank is charged charged with air until the final pressure inside the tank reaches reaches 1 megapascal. Find final temperature inside the tank. So now it's a problem of charging as I mentioned, it's a problem of charging the tank. So for charging the tank, final temperature will be gamma T. Final temperature will be gamma Tp. So this formula we have to remember. Tp, pipeline temperature, pipeline temperature, and gamma we know that is 1.44 air. So 1.4 and temperature here 350. So we have to convert into Kelvin. 350 plus 273. So this temperature will come 872.2 Kelvin, and in terms of degree centigrade we have to minus with 273, so it will come 599.2 degree centigrade. So correct answer is 599.2 degree centigrade. So correct answer is the temperature will be greater than 350 degree centigrade. So for such kind of problem where we are charging the tank, it's a kind of variable flow problem, because we are generally interested in steady flow problems, but it's a variable flow problems in which whatever the mass will enter, it will not come out. So it's a variable flow problem, and in such kind of problem, the final temperature we can find out easily with the help of this formula gamma Tp. So remember this formula gamma Tp. Here gamma is 1.44 air and Tp is nothing but pipeline temperature. Take the other problem which is asked in GATE 2007. So GATE ME 2007. I am just writing the problem first, and now then we will discuss. So which relationship is valid only for reversible. So which relationship is valid only for reversible process undergone by closed system a closed system of simple compressible substance. Neglect kinetic energy and potential energy. So now I will write the first law of thermodynamics for closed system, neglecting kinetic and potential energy. That is del Q del U, because I am neglecting kinetic and potential energy. So instead of E, I will write del U internal energy. And this one is work done, del W. And now I have to write the law for reversible process. We know for a reversible process, del Q will be TDS. Del Q will be TTS. So in place of del Q, I can write TDS del U plus del W. So this one will be the correct answer. TDS equals to del U plus